Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions from October-November 2022, paper 4, variant 2. In today's lesson, we will talk about question number 9 and question number 10. Question 9 is about quantum physics and question number 10 is from PET. And these two topics are very important for paper 4 because every year you will see one question from quantum physics and one from PET. So understanding of these two topics is very important. In today's lesson, we will discuss these two questions in detail so you can improve your conceptual understanding of these two topics and also you can have better understanding of these questions. Let's study together. Let's improve together. For question number 9, part A, figure 9.1 shows the visible part of the emission spectrum from hydrogen gas in a lab on the Earth. The numbers indicate the wavelength in nanometers represented by each line. For part A1, we need to explain how the emission spectrum provides evidence for the existence of discrete energy levels for the electron in a hydrogen atom. So first of all, if we look at these lines are representing single photons. These are representing single photons. So first thing simply we can say they are representing single photon. It is also given to you in the question the numbers indicate the wavelength in nanometers represented by each line. Mean they are representing wavelength of photons, means wavelength of single photons. So simply we can say single photon. Now we need to understand if there is an electron that is in excited state, imagine that electron is in this higher energy level and this is the excited state for this electron. So this electron will jump back to the ground state. When it will jump back to the ground state, it will emit a photon. So it will emit single photon. And the energy of this photon, we can write down photon energy in this case will be equal to difference in energy levels. Difference in energy levels. So this is 1 point you can write down in your answer. So this will be equal to difference in energy level. I mean the energy of this photon is equal to difference in these two energy levels. Now imagine that if electron jump from this energy level, let's say this electron jump to this energy level, this one. So in this case, again electron, in this case again when electron will lose energy, mean its energy will decrease, so it will emit single photon. So every time electron jumps from higher energy level to lower energy level, it only emits single photon in one jump. If electron, let's say, jump from here to here, then here to here, it will emit 2 photons. But if it jump directly from here to here, it will only emit 1 photon. Whenever electron jump from one energy level to another energy level in one jump, always it will emit single photon. So we can say photon energy is equal to difference in energy levels, and photon will have a discrete frequency. So each emitted photon will have a discrete frequency. So we can write down discrete frequency, and discrete frequencies of photons are telling us discrete energy gaps, or you can say discrete energy levels. Discrete energy gaps in hydrogen atom. So this is what question is asking you. So for the sake of this question, simply you can say 1 point you can write down change in electron energy. Change in electron energy emits a single photon. Very important point. Emits a single photon. Emits a single photon. So this is very important point you need to understand. Every time electron jump from high energy level to lower energy level, it will emit energy in form of single photon only. And the second point we can write down photon energy. Photon energy is equal to difference in energy levels. Is equal to difference in energy levels. Energy levels. And third point we can write down discrete frequencies. Discrete frequencies of photons. Photons represents discrete energy gaps. Discrete energy levels, or you can say energy gaps. Energy levels, we can say better. Energy levels. So if you write on these 3 points, you will get 3 marks. For the second part, it is given to us figure 9.2 shows 5 of the energy levels in the hydrogen atom. The wavelengths of radiation shown in figure 9.1 relate to transitions to the minus 3.400 electron volt level in figure 9.2. We need to show that energy level X is minus 1.51 electron volt. So the first thing we can do is we can imagine different electrons in different energy levels. So imagine that one electron is in this energy level and this is in excited state. Another electron is in this energy level and this is in excited state. Another electron is here. This is also in excited state. And other electron is here. That is also in excited state. Now in this case you can see when this electron will jump from this energy level through this one. So it will emit one photon, and that photon has this wavelength. Because this wavelength is the shortest, it means this photon has the highest energy. You can simply understand from here E is equal to hc over lambda. If lambda is the shortest, energy will be the highest. So this is representing this photon. Now if you look at the second one, this electron, when it will jump to this energy level, it will emit another photon, and that photon is represented by this. So this will be the wavelength of the photon emitted when electron jump from this energy level to this lowest energy level in this diagram. And the third one we can also draw. So let me redraw this one. It's not very nice looking, so we can redraw. So we can draw this proper line. So this is, and we can also clean this electron, we can clean this electron, and we can redraw. So you can see a clear picture of that. Imagine electron is here, and when this electron will jump, this will also emit a photon. So we can draw this line here. So when it will come to the lowest energy level, it will emit photon, and that photon is represented by this wavelength. And the last one, imagine that one electron is here and this is also in excited state. When this electron will jump to the lowest energy level, this will emit a photon. So we can draw this line. So this will emit a photon. Now we need to understand which one has the highest energy. So this one has the highest energy. So this is the highest energy. So we can say highest, and this one has the least amount of energy. Least amount of energy. Question is asking us to find out energy level X. So energy level X means this is the least amount of energy, least. So we can also label these energy levels. We can say this is first energy level. We can label this one is the second, and this one is third energy level, and this one is fourth, and this one is fifth one. And this photon is emitted when electron jump from X to this lowest energy level. So in this case we can say energy of this emitted photon is equal to delta E, and delta E is equal to hc over lambda. As this side is positive, this answer will be positive if you solve this one, so the left side also has to be positive. So you have to take higher energy level minus lower energy level. If you take lower minus higher, so you have to add negative sign on this side. So we can simply say in this case E2 minus E1, this is equal to SC over lambda. So we can write down E2 minus E1, and E1 is minus 3.400, and this is in electron volts. So our final answer has to be in electron volts because we are using unit for this one in electron volts. On this side we have Planck's constant, that is 6.63 times 10 to minus 34, and this is multiplied with C, and C is equal to 3.0 times 10 to 8, and this is divided by lambda. Lambda is 658 nanometers, so we have to multiply with 10 to minus 9. But this side is in SI units, so you will get this answer in joules. So we can simply say this answer will be in joules. But we want this side also in electron volts, so our final answer will be in electron volts. So we have to convert this one into electron volts. So we need electron volts, and we want to get rid of joules. So we need to understand 1 electron volt. We can simply say 1 electron volt. This is equal to 1.6 times 10 to minus 19 joules. So if I multiply with 1 electron volt here, and equivalent of 1 electron volt, this is 1.6 times 10 to minus 19 joules. So in this case, we can get rid of joules. So both sides, our answer will be in electron volts. Now simply we need to solve this one for E2. So E2 in this case will be equal to E2 plus 3.400, and we have on this side 6.63 times 10 to minus 34, and this is multiplied with 3.00 times 10 to 8, and this is divided by 658 times 10 to minus 9 multiplied by 1.6 times 10 to minus 90. Now simply you have to use your calculator, and if you use your calculator, your final answer will be minus 1.51 electron volts. So this is how you need to approach this problem. Very nice question on energy levels. I hope this one is clear to you. If you still have any questions about this one, you can leave your questions in comments and I will answer as soon as possible. For part B, it is given to us the same part of the emission spectrum from hydrogen as in part A, observed in light from stars in a distant galaxy, as shown in figure 9.3. The numbers indicate the wavelengths in nanometer. The spectrum shows the same pattern as in figure 9.1 but with different wavelengths. State the name of the phenomenon that gives rise to the change in wavelengths. So if you look at these two different spectrum, this is the spectrum in the lab and this spectrum is from the stars. Means when we observe the light coming from the stars, we see this spectrum, and these lines, they are telling us the same pattern, but only difference is that this line is at wavelength 411 nanometers, but this one is at 429 nanometers, but we observe the same pattern. Simply in this case, lambda has been increased, and this pattern is in all the lines. Means simply we see the wavelengths has been increased, but the pattern is the same. And so if we compare next wavelength, so we have 488 and here we have 509. So if we go to the last one, so this one has 686. So simply lines, all the lines, pattern is the same, but all the lines, they have been shifted by the same amount. So they have been shifted towards red end of the spectrum because the lambda in this case has been increased. So they have been shifted towards red end of the spectrum. So simply we can say this phenomenon is redshift because the wavelength of all these lines have been increased, and this is telling us that wavelength has been increased. If the wavelength increased, if you look at visible light spectrum, rho G wave, mean this side wavelength is longer, so all these wavelengths have been shifted towards red end, mean towards longer wavelength. So this is red shift, and so simply you need to write down for this one name of the phenomenon. So this is red shift. Now if we go to the second part, for the second part we need to state what this phenomenon shows about the motion of the galaxy. As this is a redshift, it simply means that galaxies is moving away. The galaxy is moving away from observers. So simply you can say, in this case, galaxy is moving away from us, or you can say moving away from observer. So galaxy is moving away. Redshift means moving away. Blue shift, if the wavelengths decrease, it means they are approaching, moving towards us. So that's all what you need to write down for these two parts. For the next part, we need to use one of the lines in figure 9.1 and the corresponding line in figure 9.3 to determine the speed of the distant galaxy relative to the observer. So hint is given to you. You need to take one line from figure 9.1, means from the lab, and then you need to take the same line in the spectrum of the star. So if you take 411 from here, you have to take 429 in spectrum of the star. So you have to take this one. You can take any line. If you want to take this, then you have to take this line in the spectrum of the star. So then you can calculate speed of the galaxy. So we have to use delta lambda. This is the change in wavelength, or you can say shift in wavelength divided by wavelength in the lab. So this is wavelength in the lab, and this is equal to V divided by C. So we need to calculate value of V. So delta lambda, in this case we have 429 minus 411. You can use any one of them. The result will be the same. Divided by wavelength in the lab. 411, and this is equal to v divided by c, and c is equal to speed of light, 3 times 10 to 8. And simply we need to calculate value of v from here, so we can say v divided by 3 times 10 to 8, this is equal to 18 divided by 411. So from here we can calculate value of v. So v in this case will be equal to 1.3 times 10 to 7 meters per second. So this is our final answer. So this is how you need to calculate. The important point is that this wavelength, this is the wavelength in the lab. So this one, you have to be very clear with this one. For part C, it is given to us the galaxy in part B is known to be at a distance of 5.7 times 10 to 24 meters from us. Use the answer in B3 to determine a value for the Hubble constant h0. So this question is simply about Hubble's law. According to Hubble's law, v, the speed of the galaxy, this is equal to h0 times t, and we need to calculate in this case Hubble's constant. So simply we can say Hubble's constant is equal to v divided by t, and v is the speed of the galaxy, and we have calculated speed of galaxy in part B. So simply we can divide this one with given distance, 5.7 times 10 to 24. So in this case our final answer will be equal to 2.3 times 10 to negative 18 per second. So this is value for Hubble constant, 2.3 times 10 to minus 18, or you can say negative 18. So this is our final answer for Hubble's constant. For question number 10, it is given to us positron emission tomography involves the detection of gamma radiation in order to identify the position of region of positrons in the body. For part A1, positrons are not naturally present in the body. We need to explain how positrons come to be present in the body during PET scanning. So very straightforward question. Simply we inject tracer into the body of the patient, and tracer consists of beta plus emitter, mean positron emitter. So simply in this case we need to write down tracer is injected into the body of the patient. Tracer is injected into the body of the patient. Into the body of the patient, and tracer consists of, or simply you can say tracer contains beta plus emitter, beta plus, or simply you can say positron emitter. So this is what you need to write down for the answer of this question. And also you can see in this picture, so this is how tracer is injected into the body of the patient. And tracer we use for PET is FDG. So this is deoxyglucose, and this one is beta emitter, plus emitter, or we can say this is positron emitter, and this is injected into the body of the patient. So simply you need to write down tracer is injected into the body of the patient, and tracer is beta plus emitter, or you can say positron emitter. For the second part, we need to explain how positrons cause the emission of gamma radiation from the body during the PET scanning. How positron cause emission of gamma radiation. So when positrons are emitted from the tracer, these positrons, they will interact with electrons already present in the body. So when electron and positron, they will meet, they are particle and antiparticle. So in this case, gamma photons will be emitted. 2 gamma photons, or we can say gamma radiations, will be emitted. Why 2? Because momentum has to be conserved. Because the initial momentum of electron and positron is 0, so the final momentum also has to be 0. So in this case 2 gamma photons will be emitted, and in this case electron and positron, these are particles, so they have mass. So in this case mass will be converted into energy. Gamma photon, they have no mass, and this process we call is annihilation. When mass is converted into energy, we call this is annihilation. And when energy is converted into mass, this is called creation. As the universe has been created from energy, means from Big Bang. So these points you need to write down. So first point we can say positron Positron interacts with electrons in the body. Positron interacts with electrons already present in the body. With electrons in the body. So 1 point you can write down. This question has 3 marks. Second, you can say, so in this case, annihilation takes place. We can say pair annihilation takes place. Pair annihilation takes place. So this is the second point. And third point, we can say, in this case, mass is converted. Mass of particles means mass of electron and positron will be converted into gamma photons. So we can say into gamma photons. So these 3 points you have to write down. If you write down these 3 points, you will get 3 marks. For part B, we need to show that the wavelength of the gamma radiation that is detected during PET scanning is approximately 2.4 picometers. And also we need to explain reasoning, because question is asking us to explain your reasoning. So first of all, let's try to understand how gamma photons are emitted. We have discussed this one in the last part. So let's try to discuss again this one. So when electron and positron, they meet, they will annihilate. So annihilation will take place and 2 gamma photons in this case will be emitted. Why 2? Because momentum has to be conserved. So annihilation of these 2 particles will produce 2 gamma photons. So we can say annihilation of particles, annihilation of positron and electron produces 2 gamma photons. So it's very important to write down. This sentence is very important because this has 1 mark. Now we can try to calculate the wavelength of gamma photon. So in this case, positron and electron, they meet and they produce 2 gamma photons. So simply we can say in this case, energy of these 2 particles will be converted into energy of gamma photon. So E is equal to delta mc squared. And in this case, 2 gamma photons are produced and electron and positron, they have the same mass. So simply we can say mass of 1 particle, this will be converted into energy of 1 gamma photon. So we can simply use mass of electron or we can use mass of positron. But mass of positron and mass of electron is the same, because they are particle and antiparticle, so they have the same mass. So this point is also very important. You need to understand they have the same mass. So we can say 9.11 times 10 to minus 31 kgs. Particle and antiparticle, they have the same mass. We need to calculate wavelength. So simply we can say wavelength of this gamma photon will be equal to hc over lambda, and this is equal to delta m. So we have to use energy of single particle, and energy of single particle is 9.11 times 10 to minus 31 kgs, and C is 3.00 times 10 to 8 meters per second, and this has to be squared because C squared. We have to calculate lambda in this case. So we can say lambda in this case will be equal to hc divided by this. So we can write down in this case 9.11 times 10 to minus 31, and this is multiplied by 3.00 times 10 to 8 square. And now we can plug in values. We can plug in values of h. H is a Planck's constant. Its value is 6.63 times 10 to minus 34, and we have C. We can cancel with this one, but you can write down the value here, 3.00 times 10 to 8, and this is divided by 9.11 times 10 to minus 31 multiplied by 3.00 times 10 to 8. You can also cancel with 1c with this. So if we solve this one, our final answer in this case will be equal to 2.4 times 10 to minus 12 meters, and this is equal to 2.4 picometers. So we can say 2.4 picometers. So this is what we need to calculate. So pretty straightforward question if your basic concept is clear. I hope these questions are clear to you. If you have any questions, please leave your questions in comments, and I will be solving remaining questions from this paper very soon. See you next video.